Well, it's a privilege to be invited to speak at this occasion, and especially I find that all the work that Sean has done in aeroacoustics is very inspiring. The new generation of people who are trying to learn about jet noise and so on. So, Sean, thanks for all the inspiration you have provided, and particularly Sean's work deals with a lot of mathematical modeling, but the style in which the work is presented, it is possible for other people to read and follow the thoughts, and then if they work hard, they can understand the mathematics. So the physics and the interpretations that are given are really inspiring. So thanks very much. So work I'm going to show some highlights from today involves some graduate students, Daniel Bedoni, Preston Ray, and Calvin Louis. And this work is supported by Boeing and the Aeroacoustics Research Consortium. So what I would like to do is start with some discussion of the computational issues that we have to face, and then use the time to show some progress in the LES of jet noise and some model problems for imperfectly expanded jets. So off the top, we have to realize that jets that we would need to deal with will be either pressure matched or mismatched, and in the case when they are mismatched, there would be a shock cell structure that would need to be represented. And as far as turbulence is concerned, we would have to think about the multi-scale nature of turbulence. At any location, we will have scales that are most energetic. Thinking about the jet as a whole, there will be scales that would be the scales that are globally most energetic, and there would be motions that are still larger than the largest scales, and in Townsend's terminology, these are called large scales. And just to make sure that the notion of large scales is not confused with the notion of large scales in large eddy simulation, where large scale actually means to energy containing scales. These are scales that are larger than the energy containing scales. That's why I've added the word very in front. So we would have noise, mixing noise from high-speed jets, example from Jack Steiner's beautiful pictures here, and shock-associated noise arising from interactions of shocks with the turbulent shear layers seen here in terms of these cylindrical waves. We saw these pictures yesterday, I believe. So in doing computations of these problems, we have to recognize that there is a disparity of scales. Turbulent scales are usually much smaller than the acoustic scales. Wavelengths of sound are larger by a factor roughly 1 upon Mach number. And there is a much greater disparity in the amplitude of turbulent motions versus the sound that those turbulent motions produce. This is the basic aspect of aeroacoustics, that turbulence is a very inefficient producer of sound. And so if we are to compute it, we must pay a lot of attention to the numerics to make sure that dispersive errors and dissipative errors are minimized so that these small amplitudes of sound that are produced by turbulence can be calculated in a reasonable way. Even more critical is the issue of boundary conditions. We need to make sure that the calculations are such that we are able to provide exit of vortical disturbances out of the flow domains in a silent fashion. We would also need to specify inflow conditions that are silent, that the act of specifying some incoming disturbance doesn't produce a large amount of sound. And this is particularly critical when we're trying to specify inflow, which is a turbulent inflow. The flow domains would generally also need to be surrounded to reflect the ambient medium in which the flow is taking place, because we cannot afford to really simulate the entire region of the flow and the ambient, and so we need non-reflecting absorbing boundary conditions. So the message is that we need to make sure that numerical artifacts are well under control, that their effects are minimized, so that we have some physical confidence. And I cannot stress this point strongly enough that this is a very critical step. So with that, I will now continue. In year 2000, Jonathan Friend published a very nice study of direct numerical simulation of a low Reynolds number near sonic jet. And since that time, he has used it to explore questions about sound sources in this flow, and is being used for getting a better understanding of the noise sources. At Stanford, we have been undertaking large eddy simulations of jets, and this is what I will show you results from. And the notion here is that large scales or energy containing scales of the jet are directly captured. Only the small scales need to be modeled, and there is good hope that models of the small scales, because small scales tend to be universal, can be more robust and less dependent on the details. Nozzle geometry can be included in the calculations. This is where current work lies, of including the nozzle geometry, so that the turbulent energy containing motions, how they are impacted by the nozzle geometry, can in fact be calculated as a result. This has not been achieved yet, but this is where the current sponsored work lies. So the results I'll show you, they are being benchmarked for noise predictions in terms of their capability vis-a-vis the experimental data that is available. So we have conducted simulations over a range of conditions, Mach numbers going from subsonic to supersonic, acoustic Mach numbers of the jet from from low values to supersonic values, and cold as well as heated jet conditions. So these conditions have been chosen so that we can try to match experimental data that is available. Results I'll show don't have any nozzle, and so we try to mimic the effect of the nozzle by inflow conditions, and I'll explain how we're doing that. We will see that the resolution that we are able to afford is such that the turbulence that we calculate there is no turbulence beyond the Strual number, and therefore there is no sound beyond that Strual number as well. Of course, if we increase the resolution, capture the early shear layers which have the higher frequencies, one would have the higher frequency sound as well. So this is one picture of a computed flow field. This is a near sonic jet. We see in the middle contours of vorticity magnitude showing the turbulence that is developing in these shear layers, and the potential core ending here, and then the turbulence as well as the mean velocity is decaying downstream. And overlaid here are contours of divergence of the velocity, dilatation, showing acoustic waves that are generated and radiated away from the jet. One can see that it's this region of the jet where the potential core is collapsing, that the dominant noise is being generated. I have a movie and movies on other flows like this that I can share with you later on if you're interested, but I think we can imagine the waves that are being generated here. Or we can move on so that we have time to discuss things later. So how is this flow produced? We take a mean flow profile at the inlet, such as written down here with the specified momentum thickness, to which we add a large number of eigenmodes of the linear stability equations, which is the compressible Rayleigh equation. Typically, we use something like 48 modes at different Strual numbers and different azimuthal mode number. And the forcing level for these modes is chosen so that all modes are given equal democratic vote. They have the same amplitude, and the total of the streamwise fluctuation that they produce is the level that we target. So here I'll show you results where we have forced so that the peak streamwise fluctuation is 3% of the mean velocity. So we set a target level, and then we force all modes to have equal amplitude, and let the jet flow or the mean flow decide however it wishes to evolve. And so this is a matrix of conditions that we have simulated that I showed you a range of acoustic Mach number 0.5 going to 1.5, and cold and heated cases. These are the Reynolds numbers. Note that these cases correspond to these test points from TANA. Of course, the Reynolds numbers are not matched relative to TANA's cases, where the Reynolds numbers are considerably larger. So here's one example of an overall calculation shown by the streamlines that are computed from the mean flow. And as the jet spreads, centerline velocity decays here, potential core is ending here, fluid is being entrained into the jet from all sides, and in particular, fluid is also being entrained from the inlet region, as we would want to happen as well. So from it, this is sort of a busy slide where centerline velocity as a function of downstream distance has been, attempt has been made to collapse it for all the simulations that were listed on the previous chart. So Mach number is varying, heating conditions are varying, and attempt is made to compare to experimental data. So let me walk you through this. In this group of points here, first let me explain the color coding here. The blue points correspond to unheated jets, and the red points correspond to the heated jets. If you look carefully in here, we will see that DNS results of Jonathan Fren, LES results of near-sonic cold jets from the Lyon group, and our LES results for the cold cases all lie in there. These are the heated cases, and I should explain further that this includes this parameter kappa and this potential core location x sub c, which are taken from Witzig's correlation of heated and compressible jets. And so if you compare individual cases, they will be shifting. Potential core length increases as you increase Mach number, potential core length reduces as you heat the jet, and so on. All of those trends have been taken out by using Witzig correlation. And so the point I want to make is that things behave in a way that is similar, and we will see more of this later on, but there are some differences that one can see as well, that relative to the collapse of the experimental results here, the LES results are showing a little faster decay of the central line velocity, which is also seen in this DNS. And the reason we suspect is that since the forcing is due to jet column modes, from the experimental information that is available where jet column modes were forced at higher amplitudes, this trend is also seen, that forced jets with jet column modes show a faster decay of the central line velocity as well. But a more detailed experimental investigation might help sort this question further. So if I show you this for turbulence intensity, streamwise turbulence as a function of downstream distance, again, a similar representation. Density deficit in the jet as a function of downstream distance, cold cases and hot cases. The trends that are seen in the experiments are observed in the simulations, that as the jet Mach number increases, peak RMS intensities decrease. As jet is heated, things shift upstream, intensities increase a little bit. All of these trends that are seen in experiments are found here, although there is some perhaps quasi-laminar behavior in these calculations still. Turning our attention to sound that is computed in these calculations, this is the high-speed jet case, cold and hot. The symbols with line passing through are the simulation results, and the other symbols, which don't have any color added to them, are the experimental results from Tana and from Dennis McLaughlin's group for cold and hot conditions over here. And you can see that the simulated results, which have been projected to 100 jet diameter from the jet, and likewise these data points have also been extrapolated to the same distance, that there is a rather satisfactory collapse of directivity. If you look at it more carefully in terms of the spectral content, again, the blue is the cold and red is the hot, and open symbols are cold experimental data, and filled symbols are the hot case from Tana, that there is satisfactory agreement of the spectral shape. These are 1/3 octave spectra that can be computed from the simulated results. We're also grateful to Vichy from Boeing, who shared with us a narrowband spectra from near-sonic cases here. And when we compare our simulation results, which are these curves in blue and in red for the heated case, to his experimental data, we see that, again, trends that are seen in the experiments are followed, but this is bringing out a very important point, that there is a Stowell number here above which the simulation results fall off dramatically relative to the experimental trend. And so we've looked at why this is and how can we describe the onset of this fall off, and we find that the onset of this fall off is related to the turbulence that we have represented in the flow. As I said before, we don't have turbulence which has frequencies exceeding this, and so therefore there should not be any sound at frequencies that are larger than that Sewell number. It is not some numerical dissipation of sound. It's not due to some inadequacy of the numerics. It's just that we have done these calculations with relatively modest resources. We're not trying to do a very expensive, the state-of-the-art large calculation. These are done with 1 million mesh points. So it's a very affordable calculation. And with that 1 million mesh points, we are showing that there is up to a number of 1 or so we can capture the frequency spectrum. If you want to pay more, you put 10 million mesh points, this bandwidth will increase as a result. And of course, 10 million mesh points is also affordable, but you just have to be more patient with the turnaround on a computer. So to summarize these LES results, plume properties I didn't show you in detail, but we have papers. We presented this at Manchester meeting, and there will be more discussion at the Monterey meeting as well. These trends I observed here, a low-pass nature of the LES spectra I stressed, and we are now using this database more in detail to see how we can try to understand the sound generation. Break down the fluctuations into energy-containing and larger than energy-containing scales. Look at organization at scales which are many times the jet diameter and so on. See if we can understand that. So I will switch gears now and turn to jets which are not pressure matched. This is sketched from Dosanjh Yu, and this figure is very much like a picture I showed you previously from Jack Seiner's Schlieren images. This is a picture from Yulu of showing the generation of screech noise from the oscillations of the jet, which are associated with the growth of the instability waves interacting with the shock cell structure, producing these strong acoustic emissions. So in light of these sorts of experimental observations, we have looked at some model problems, and so I will describe those model problems. But before I do that, let me say a few words about previous work in trying to model screech as well as broadband shock associated noise. For screech, the pioneering work of Alan Powell established the basic mechanism of screech, and that turned into the discussion of different elements of time delay that all add up to an integer multiple of a basic frequency, gives rise to a formula which is very satisfactory in predicting the screech frequency as a function of operating conditions. And TAM has made some further modifications to this formula. And so this is well in hand. It works very well. Lots of conditions have been looked at by TAM in a lot of detail. For amplitude, there is no simple model, although there is good reason to expect that one should be able to develop such a model. Perhaps a low-dimensional approach would be a good one to use. What has been done are very detailed nonlinear calculations where the nonlinear equations are solved, including the nozzle and so on, and have shown trends that are seen in the experiments. But the next step would be to try to reduce it down to a simple model. In broadband shock-associated noise, the pioneering work of Harper, Burney, and Fisher in 1973 has been the cornerstone of thinking about broadband shock-associated noise generation, and work of Howe and Fox-Williams is a great inspiration in trying to interpret how sound is being generated in these problems. And I'll connect to this work a little bit more as we go along. Tam and Tanna took the approach of describing the sound generation as a Mach wave emission process, and that led to a model which was used in Tam's later work in the late 80s in the development of a semi-empirical model, which has been very successful in trying to describe broadband shock-associated noise. So the model problem that we have derived from this type of observation of how sound is generated takes the shear layer and considers the interaction of that shear layer with an imposed compression wave, which reflects as an expansion wave from the sonic line over here. So the difference between the real problem and this model problem is that we surround the domain by boundary conditions which absorb these acoustic waves. And so once these acoustic waves are absorbed, there is no feedback between these acoustic waves and the shear layer disturbances. So by that process, we have essentially eliminated feedback and we have opened the loop. This problem has feedback and operates in a closed loop fashion. And so by eliminating this feedback, we can now have a way of studying a sort of the system response in an open loop fashion. We can prescribe shear layer disturbances at will, we can prescribe this compression wave at will, and that interaction produces the sound, and we can study the characteristics of that sound. We can see how the sound depends on the shear layer characteristics and how it depends on the compression wave characteristics. And so Ted Manning, in his work on this problem, showed that as the shear layer rolls up into these clumps of vortices, when the strain of vortices passes over this compression wave in the region in between the vortices, the tip of this compression wave escapes and leaks to the other side. I'm using terminology that is inspired from Howe and Fox-Williams' work. We saw this, but as you will see, by some further analysis, we come with the use of words that I just did. By varying the shear layer amplitude, we see that for small shear layer amplitudes, the radiated pressure is in fact proportional to the forcing level, but more interestingly, above some amplitude, there is a dramatic exponential dependence of the radiated screech amplitude on the shear layer disturbance. And even more strikingly, at larger amplitudes of the shear layer disturbance, there is a saturation. This radiated amplitude does not increase anymore. These are trends that were anticipated in the work that I've been citing. And Takao Suzuki took up this problem in trying to model the shear layer as a slowly varying medium. A shear layer has vortices. Those vortices are growing and amplifying as you go downstream, describing them as a slowly varying medium, slowly varying both in space and in time. And consider the problem of interaction of a weak shock, that's the shock that is prescribed, its interaction with the slowly varying medium analytically, and this is done by essentially WKB type of approximation. Shock is represented essentially as a step function, step-like function whose thickness is becoming very small. And so by taking appropriate limits, one can show that at leading order, in fact, for this weak shock, one gets an Eikenel equation as one would in rate acoustics or geometrical acoustics, and at next order, one gets the same equation as the transport equation. So then by solving this Eikenel equation and transport equation by methods which are essentially the methods of geometrical acoustics, one can predict the outcome of the interaction of a weak shock with this medium which has vortices, traveling and growing vortices. And the outcome of it is going to be shown in the next few slides. Here, in terms of geometrical acoustics, we can see where the rays go, and in the early portion where the shear layer has not yet rolled up, these rays undergo total internal reflection. All of that sound is turned back into the flow, but as vorticity clumps and creates these vortices, in between them are the regions where these rays are not turned around. They turn around, but not enough to go back, and so they are able to escape to the other side. And so quantitatively, now this is the direct numerical simulation. Contours of dilatation are showing this wave that is being generated by the interaction of these vortices with that wave system. This is the wave that has resulted. And next picture will show that geometrical acoustics also predicts the same wavefront, same shape, and its propagation. There's a nice movie that I can show later and so on. And amplitude and directivity that we compute is also well described by this geometrical approximation. So the next step was to consider a turbulent flow problem where the shear layer is now turbulent. This is a three-dimensional calculation, much more expensive calculation, using about 20 million mesh points. And so we have not been able to do too many of these. Interaction of this turbulent shear layer with this compression expansion wave system produces now broadband noise, which is propagating upstream. So we have looked at characteristics of this sound. And if you're interested, there's a movie I can show on this later as well. So we have looked at the space-time correlations of the turbulence in the region just upstream of that interaction, so that we know what are the attributes of the disturbances that are interacting with that wave in order to produce the broadband noise. So one feature of the noise that is produced is striking, and I would like to stress it here. This is the sound pressure spectrum plotted as a function of frequency on a logarithmic scale. And because it's linear here and logarithmic here, I pre-multiply it by the frequency, which is a classic way of stressing where the energy is. And so we see that the energy here is at a Strouhal number defined in this way at a number of 0.05 or so. This is a similar spectrum of the turbulent fluctuations near the interaction region, and we see that the turbulence peak is essentially at the same frequency as the frequency of the sound that is produced. Spectrum of second time derivative of the turbulent fluctuations at the local point, of course, have a frequency peak which is much larger than the sound frequency. So it's not this which is going to explain that sound. And so there is some thinking required to see how one can explain that theoretically, and so I'll get to that in a second. So summarizing some of the observations, we find that sound that is generated by this isolated interaction is essentially omnidirectional. We were able to vary the amplitude of the imposed wave, and we verified that the amplitude scales with the imposed delta P. A peak frequency of the noise was found to scale with the peak frequency of the turbulence. And another phase relationship was observed. Okay, so I will wrap up very soon. So we have taken an approach of trying to describe the sound generation by considering the interaction between unsteady disturbances in the shear layer and the stationary wave disturbances. And analysis of the early region indeed shows that there is sound spectrum would be proportional to the spectrum of the turbulence. And so how that comes about, I will just explain by considering a little region of that interaction, and flow variables in the stationary wave have prescribed variations. Pressure goes up through this wave, stays up, and then falls back down to the original value after the expansion wave. And so using a very simple representation of that wave, in the context of a wave equation where we have the source terms associated with the interaction of the turbulence with the stationary wave, the point to be made, and this is where Sean's work is very, very inspirational to see how to treat generalized functions in a careful way. Terms that involve surface integrals are large relative to volume integral terms and so on. Some math that I will skip over, leading to a final result that the radiated pressure, when scaled with the delta P associated with the incident wave, has a very simple representation, that it is the turbulence that is going into the interaction region evaluated at a retarded time divided by the jet velocity, has a proportionality factor which involves this delta P of the incident wave and a correlation length in the span-wise direction of that turbulence with a proportionality factor. So this is interesting because it has certain implications. P prime is proportional to delta P. A simple direct relationship by means of acoustic analogy, at least I haven't seen derived. I'm sure it is in Sean's work, but that model considers a much more elaborate problem than the simple one that I'm considering here. This also indicates trends that have been suggested in the experiments, but there continues to be discussion in literature, and it would be useful to look at these more carefully. So I want to end by indicating that we have also considered more complete model where we solve numerically the linearized Euler equations, where source terms are the bilinear momentum fluxes involving the interaction of instability waves with the shock cell structure. This is essentially a numerical solution to a problem that Tam in his paper posed. It was not possible at that time to solve the problem. Now we have effective numerical ways to solve that problem. And so if we do solve that full problem, in here, instability waves are growing in the form of a wave packet and decaying. I haven't shown that. I've just shown the acoustic field at Stowell number of 0.5. The acoustic field that is produced radiates in this upstream direction. As we increase the Stowell number, the radiation direction shifts. These are trends that are seen experimentally, and there is a simple expression or reason why these angles change in the way they change that have been explained by previous workers, and this is very much consistent. So I would like to end by saying that DNS and LES is a very useful tool, and the part that I would like to stress is that we should use these tools to advance the science of aeroacoustics, the fundamental processes of sound generation in a variety of problems of interest to aeroacoustics. And it's here that a paper of Sean was very influential in re-stressing or keeping us focused on this. Sean's advice was that as people work in this field, that they keep themselves to simple problems and not worry too much about practical application at this stage. It would have been nice to put that quotation, but he says that don't worry about application at this stage. Do simple problems first. Applications will come down the road. So thank you.
Okay, I think we're just going to move straight on, unless we can have one quick question whilst I'm getting my talk. Is there a question from the audience? Yes.
Yeah. I'm not an acoustics man, but Sir Paul is from Boeing Company. The interaction between the vortex and expansion wave, is that unique to this work, or has this been proposed before?
No, it's in this work. It's unique in the sense that it is the interaction of this compression expansion wave reflection problem. There have been a number of previous studies where the interaction of a vortex with shock has been looked at. Harv Ribner did modeling studies of it, and there have been experiments over the years seeing sort of the quadrupolar sound that is produced by the interaction of an isolated vortex with a shock. But here, the vortex does not penetrate through the shock, but it is essentially flowing in the shear layer, and the interaction is of a different kind, because there is an ambient medium in which sound that is generated can propagate, whereas when vortex punches through a shock, it finds itself in a different region altogether. That's a different problem, but that has been looked at.
Okay, thank you.